All right, let's see here. I will begin with a word of prayer. Dear Heavenly Father, we just thank you for this day and this class. Just pray that you'd bless our work here, help us to understand what we need to about the solution to test 2. Just pray that the students would be encouraged to fix whatever mistakes they made, that they do better on the final. And we just pray that you be glorified in all that we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me blow this up a bit here. So problem number 1, calculate the electric field given that the voltage is as such here. So we simply remember the electric field is the gradient of the voltage function times -1. So I take the partial derivative with respect to x for the first component. Now the only thing that matters is this term because there's no x dependence over here, so I can just take that derivative. And for the y derivative, only this piece and that piece matter because there's no y dependence there. And likewise, there's only a z dependence over here. So that gives me minus 2ax here, and this minus gives me plus. Partial derivative of y with respect to y is 1. That gives me b, and then over here also minus plus, and this differentiates to give me a c. And then over here, I get a minus is plus, and the partial derivative with respect to z of z is 1, so I get a c over here as well. So that was that. And a lot of you guys got that. Or you got close, and there was some minor mistake you made in there. A lot of people. This one here, I think most people, if they got it wrong, probably fell prey to a calculator mistake, most likely. I wasn't trying to make this easy. It hadn't dawned on me that the triangle is way easier than the square. Man, I should have made it a square. Square, at least you got to think, but the distance between all 3 charges is all L, so there's no geometry in here at all. It's too easy. Why put this problem in your chest? I'll tell you what. Anyway, so I decided to make Q equal to 10 nanocoulombs, and so I got 1 times 3, 1 times a 4, and finally 3 times 4, which of course gives me respectively 3, 4, 12. Sum of those, we get 19 kq squared, which when we plug in the numbers, we get 6.099 times 10 to the minus 5th joules, also known as 60.99 or 61 if you like, microjoules. So there's that. Yeah, you guys could work on this one a little bit. And this shows a deeper weakness, I would say, in that it shows that a lot of you still don't really have a mastery of Gauss's law, which is a problem because Gauss's law will be a major topic on the final, I guarantee it. So, you know, you need to figure out what you're doing wrong here and fix it. So like, to figure out the electric field inside this spherical shell of charge, I figure out the charge enclosed. I take the volume of the spherical shell, in this case r cubed minus big R cubed, divided by the total volume, which would be 2r cubed, which is giving me 8. 2 to the third power is 8. 8r cubed minus r cubed, that's what is known as 7r cubed, which gives me, well, that equality. And then solving for E, this is the Gauss's law, so the flux divided by epsilon naught is Q enclosed. Q enclosed over epsilon naught is equal to the flux. I multiplied epsilon naught over to the flux just to have an equation here. Anyway, so I solved for E as a function of R here, and that gives me this lovely thing. I decided that I didn't want to keep writing this over and over and over again, so I called it alpha. So I get V as a function of R by integrating this, alpha times R minus R cubed over R squared. Integral of R is R squared over 2. Integral of R cubed over R squared is minus 1 over R, but the minus cancels and you get a minus a plus. I keep the minus outside, you know, got to put it somewhere, so there it is. And then plus V naught, because when we integrate, we add a constant. That constant's important because you need to fit that constant to be whatever it needs to be in order to make the voltage 0 at the origin, as was requested in the problem statement. As you can see right here, 0 at the origin. So notice that the electric field is 0 inside the shell because there's no charge there, so a simple Gauss law application will show you that Q enclosed being 0 means the electric field must be 0 there as well by the spherical symmetry of the interior region. And as such, the electric field is 0 inside, but if the electric field is 0, that means that the voltage when differentiated with respect to the spherical radius here, must also be 0, which is to say that the voltage must be constant. But the constant has to be 0 because it was given to be 0 at the origin. As such, the voltage in the shell must also be 0 when you get to that edge right there, right? It must be 0 at R equal to big R. So I make that happen by choosing an appropriate value of V0. So I make this equal to 0, solve for V0, and gives me this 3 alpha over 2 R squared, and then I just decided to factor out the alpha and write it back out, just so I'd be able to see your answers in comparison. If I write my answer in terms of alpha, it's hard to grade with this answer, so I put it back in terms of that mess. And, well, I think one person got this, and one person got close, and yeah, a lot of people missed this one by a lot. So, yeah. So anyway, you guys should work on this one. And problems like it, like we worked one like this, but we made the voltage 0, I think, at infinity. But here I made the voltage 0 at the origin, which is a little bit different. Most people got these. Hooray, hooray. So I worked them and made them 42. So you got 10 in series with 10 gives you 5, of course. 5 microfarads plus 37 microfarads, 42 microfarads. And here, 8 paralleled with 8 gives you a 4. 11 plus 4 is 15. 15 plus 27, also 42 kilo ohms. So you got those. Most students got these. If you missed those, you need to work on them. Down here, less success. So essentially, the point of this problem is that if these capacitors are open circuits, it's effectively just like you've got R, R, and R, which is a series combination of 3 resistors, which makes the current 9 volts over 3R. So then if I want the voltage at VB, it's IR, but that is, well, the R's, they be canceling. And so as such, we get 9 volts over 3, also known as 3 volts. So we get 3 volts at B and also 6 volts at A, depending on how you want to look at it. I looked at it 9 minus 3 is 6. Of course, you could also look at it as IR plus IR, which is 3 plus 3 is 6. Now, on the other hand, the voltage at C is not 0. It's more complicated than that. Think about what the equivalent capacitance here. Well, the equivalent capacitance happens to be 0.8 C by this calculation right here. And on the other hand, it's equal to Q over 6 volts, you see, because 6 volts is the voltage at A. So there's 6 volts dropped across this capacitor, series capacitor. As you know, capacitors in series must have the same charge on both. So if I can find the charge on the equivalent capacitance, I can find the charge on each of the capacitors forming the equivalent circuit. As such, I get this, it gives me a formula for Q is 4.8 CV, but then the voltage on the capacitor, which is the voltage at C, is also Q over C, which gives us 4.8 volts. So I think nobody got this, but there it is. Now, if you build this circuit and find a different voltage than I have calculated here, let me know. But I think this is right. I'm pretty sure. Now this over here I'm more certain of, because you've got 10 volts and 30 ohms. So by Ohm's law, 10 volts divided by 30 ohms, 0.3333 amps. Yep. And on the other hand, if I do the voltage, do the loop here, I get 10 volts minus the current through the 20 times minus 5 volts equal to 0, which of course means that, and you could also just look at this like this, right? If I got 10 volts here, I got 5 volts here, that means there must be 5 volts there, just by comparison, thinking about how voltages add and so forth. But anyway, it's 5 volts divided by 20, 0.25 amps, and there you go. Many of you guys got this, not everybody. It's a mix. Let's see here. Yeah, so a lot of people set this up mostly right. A lot of people, probably about 5 of you who had a sign error in this part. More of you had a sign error somewhere in this thing. Some of you just, messed up the algebra somewhere, who knows where. So yeah, there's a lot of partial credit earned here, a lot of signs of life. It's hard to get these exactly correct. It's just a pain. It is what it is, but these are the answers: 2.087, 3.304, and 5.391. And the reason these are, there's a minus here, milliamps is because I have omitted units of kiloohms in volts. So 1 over, you didn't divide by the resistance, divide by kilo, you get a milli. So these are in units of milliamps when you backtrack on the, and the answers must have units. Like I'm okay with calculations not having units, but answers must have units. And if answers don't have units, I will take off points. This down here, let's see here. So I have the math derivation over here. Now you could have just written down the, you could have just wrote the solution and then fit the initial conditions. I would have been fine with that. But here's the math. It's like, you know, this is the Kirchhoff's voltage law, which then you do integrating factor method on, and whammo, that's what you get. But the charge is 0 at 0 because the switch is initially open, which makes you find that C1 has to be minus V naught C. And this formula is 0 when we plug in time 0, 1 minus 1, 0, so it checks. All right, great. Now the current is dq dt, which when we calculate we get V naught over R times that. But on the other hand, the current at time 2 is 1.00 milliamps, but that's also V naught over R, e to the minus 2 over RC. Now I could put a second here if I wanted, but I just didn't. Sorry, I know I'm kind of being inconsistent in my partial use of units, but well, anyway, sorry. But now R times C, oh, I don't know that yet. So I take the natural log of both sides. This is 0.2 actually. And so I get minus 2 over RC is natural log of 0.2, which works out to give me C is equal to minus 2 over 100K times the natural log of 0.2 farads, which works out to 12.43 microfarads. I think a couple of you got this. That's good. Many more of you did not get that. And then to figure out the energy, we can use Q squared over 2C because we already know Q. Or we can calculate Q. I mean, there's various ways to do this. 1/2 CV squared. But if you use 1/2 CV squared, you cannot use the 500 volts because 500 volts is not the voltage on the capacitor. As such, that equation is nonsense. But Q at time 2 is the charge on the capacitor at time 2. And so I plug it in and I get 0.9944 joules, or about 1 joule. I think I did ask for the energy at, yeah, the energy stored in the capacitor at time 2 seconds. So to be reasonable, you'd have to figure out what's the voltage stored in the capacitor at time 2 seconds. 1/2 C times that voltage squared would have been the energy, not the 500 volt. 500 volts is the total voltage applied. That's not the relevant voltage to figure out the energy in the capacitor. I know that'd be nice since you actually have that number to work with, but that's not how it goes. Now here, I thought this problem had a nicer answer, and I was wrong. So everybody should have written this much down, like what's the voltage if you've got a charge at the origin and a charge at X naught, Y naught, Z naught. Well, this is the voltage for the charge at the origin, right? Minus Q naught at the origin, plus KQ naught divided by the distance from X to X naught, Y naught, Z naught, I mean XYZ to X naught, Y naught, Z naught. That's the voltage by, we've done a bunch of these. So that's the voltage at XYZ, just like that. And if I want to figure out where else the voltage is 0, I mean, this makes the voltage 0 at infinity, of course. If I want to find out where else the voltage is 0, I simply set 0 equal to that and work it out. And yeah, I don't know. There's probably, I might be able to see another way to look at this. Well, here, the one other thing come to mind to me, like earlier today. There's probably, I'm not done thinking about it, but so I could look at it this way: X, Y, Z dot with X naught, Y naught, Z naught. That gives me this term equals to 1/2 X naught squared plus Y naught squared plus Z naught squared. I'm not sure geometrically what this thing is. What does it mean if you have the dot product of, you know, a dot product with a fixed vector equal to a fixed value? Like, what is that the equation of? I don't know offhand. Let me turn the light on here in a second and we'll see what I wrote. I feel like it might be a cone. Maybe it's a plane. Is it a plane? Oh, it's a plane. It's a plane. I'm an idiot. Come on. Good grief. This is why I need to be teaching Calc 2, Calc 3 right now. But this is, all right, so this would be, what is this? This is the plane with normal vector, x naught, y naught, z naught, right? And yeah, that's what it is. So, oh, no. Well, yeah. No, that's it. I think that's it. Now, let me not, I'm not going to talk myself out of it. It's a plane. It's a bird. Well, anyway. Let me move on here. Final problem. Where'd my laser go? Oh, here it is. So if you got 20 kilogram mass initially at the origin with this velocity, moves to position 1 minus 3,2 under the influence of a force due to the electric field with a potential blah, 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 where, all right. So if the mass has speed 0 at the end of this motion, then find the work done by the net force over the motion. So I'm not trying to say that the electric force is the only force. In fact, it's pretty obvious it's not if you work out part B, because the work energy theorem, which is independent of the details of the force, we know that the work is the change in the kinetic energy, and I gave you more than enough information. Well, I gave you enough information to figure out the change in kinetic energy, because it's 1/2 mvf squared minus 1/2 mv naught squared. And Vf is given to be 0, and V naught is given to be, well, the square of it's 30 squared plus 40 squared. And this works out to minus 25 kilojoules. So minus 25,000 joules, which some of you guys got. Yay, very good. So you're like, we haven't talked about this. Well, I don't know if we have or not, but this is physics 1 that you're supposed to know. And if you don't, you should review it. You can come ask me about it in my office hours if you want. I can answer questions. The work done by the electric field is minus Q times the change in voltage. I gave you the voltage function right here, and so you just gotta calculate, and yeah. So the alpha is just a dimensional multiplier, and so we end up with 1 minus 9 plus 6, which is otherwise known as minus 2. Minus 2 times 30 is minus 60, so we get minus 60 microjoules, which not many people got. So that's unfortunate, because that actually wasn't that hard, but it just looks scary, I guess. And you guys were out of time. I get it. I mean, there wasn't enough time probably, but anyway, I hope you can see that every problem on this test was very much within your grasp, perhaps except for problem 3. Problem 3 was actually the most challenging problem, but it's also the problem which is maybe most likely to reappear on the final. Not this problem exactly, but problems like it, because I have to ask questions like it. Otherwise, you guys would just copy formulas down, and then I feel very, very silly. Anyway, have a good weekend, guys. And I'll see you Monday, I guess.